Ok, comenzamos. Gracias a todos por venir. Gracias también a David, nuestro speaker, por aceptar la invitación a dar la charla en el seminario. David es un destacado investigador de la Universidad del País Vasco en España y también del Centro de Matemática Aplicada del País Vasco. Hoy día nos va a hablar de Challenges when Integrated Neural Network for Solving Parametric PDEs. Eso creo que entiendo que David va a dar la charla en inglés.
Guys, whatever you want English. English
is fine.
Yes, that's fine. That's why I'm looking at him. Good.
Okay. So let's welcome David.
Thank you very much, Manuel, for this invitation. Thank you very much to all of you. I'm very glad to be here. But I didn't do this presentation, okay? I'm the last author. The first author, Jamie, is the one who really did most of this, okay? It's several papers on integration and on integration of neural networks. And let me go ahead and start going, to what I want to explain. First, for those of you who are not familiar with solving partial differential equations with neural networks, I'm going to provide an introduction. I'm going to talk about 3 general challenges that occur when you try to solve these PDEs with neural networks, these ones. And then I'm going to focus on this one, on the integration, okay? And this is the part I want to explain very well. I will spend most of my time here. And then these are some options we proposed to solve the problem of integration of neural networks when solving PDEs, but you can use different ones. I will go very fast with that and very fast with all of that, okay? So the focus is really in this part 3.0 of BPIN's findings against integration, okay? Interrupt me at any time, any question you have, you tell me. Okay, functional analysis. Sorry if I make any mistake, okay? So I go slowly. Basically, the solution of a PDE can be seen as a zero of this residual operator. So we consider here the Poisson equation, then we can consider this in a strong form. And therefore, we have this. This will lead, we will talk later, to the so-called pins. You can also consider it in the weak fashion, and you have this variational formulation, the standard one, okay? So, if we think in terms of residual minimization, we want to minimize the residual in this dual norm. In the strong form, you have this thing, which is the dual norm of the L2 is L2. So we are just minimizing this. This is what pins does. And in here, we have to minimize this residual norm in the dual norm, which is in the H-1 norm. Okay? And as we will see, variational pins try to do that. Okay. This is so far just functional analysis. So the entire point is that we want this residual in the dual norm to be equivalent to the error in the energy norm. And for that, we want to find these equivalence constants, M and gamma, and we want them to be robust, that is, to be as independent as possible of all the parameters of my PDE. So hopefully to be constants as close as possible to 1, okay? So the entire thing on the functional analysis to define a good estimate of this residual in the dual norm is intended to get these constants right. This is basically this. And as I said, if you consider the strong form of this residual, you end up with pins. If you consider the weak form, you end up with variational pins, or if you want the robust version of variational pins, published by Sergio. You can also do weak adversarial networks, where you try to find the optimal test function with another neural network. Then it's not exactly the same, but the deep reach is also related to this weak formulation, and then there are other papers similar to that. And you can also consider, by the way, the ultra-weak formulation, where you can do something very similar. Okay, there are several papers of that, but I don't want to focus on this part of it, unless you have any questions. So then the next idea is, okay, so far this is just functional analysis, and the idea is to replace U by a neural network, and that's when it comes all of these PDE solvers using neural networks. Okay, so with the neural network, you have an input, which is the space variable x, 2D x and y. You have a neural network with some trainable parameters. You end up with some estimate of your solution. You compute this loss, which is this residual in the dual norm, or an estimate of that. And then you try to minimize that. How do you try to minimize that? With a gradient descent algorithm. That is, you minimize this with a gradient descent, and you keep changing those weights until you find a solution that makes this minimum, or that you achieve this minimum, or you get close to that. Okay. I'm not going to enter into the fact that you have quasi-minimizers or something. Just I'm trying to keep it simple. Okay. So, in my mind, there are three main problems that occur when you try to apply this technique that prevents you to obtaining good solutions. Okay, because if you try to do a software with that and solve a PDE, typically you get really, really bad solutions. That's the standard thing. Okay. What
do you mean by good and bad?
Well, good and bad means good error 5% or less, bad error 75% or more.
Yeah.
You get trash, complete trash. This is the typical thing. For a 1D problem Poisson equation, complete trash. And there are mainly three issues in my mind. Okay? The first one is very simple to understand, which is the fact that you are doing a gradient descent algorithm. So if you do a gradient descent, you start here, you end up in a local minimum, not in a global one. Okay, and this is a major problem of all artificial intelligence algorithms. Okay. Initialization is critical. If you start here, you end up with a good thing. If you start here, you end up with a worse thing. Okay. That's part of life. This is something very basic that you learn in mathematics at the very beginning. Right. By the way, people from artificial intelligence, oops. Renovar o desinstalar, what do I do? I don't know, you tell me. Or you know. Okay. People from artificial intelligence, they typically believe they end up with a local minimum that is good enough. This is the general assumption. Okay. Okay. So one simple thing we can do is the following. You can think of solution as a multiplication of these coefficients times the solutions on these basis functions. Let me call them basis functions even if this is not a basis, okay, or these functions, let's call them. And if you do that, you can see that the U is linear in the coefficients, and because this is typically a residual square, that implies that this loss is quadratic in U, which is linear in C. That means that the loss is quadratic in these coefficients. If the loss is quadratic in these coefficients, you can solve it with a least square system in one shot. Okay? And therefore, what you typically do is you think that the neural network goes all the way here, only here, and the rest is part of the loss. And the loss implies solving a least squares, finding the optimal coefficients, and then finding this loss. And if you do that, okay, basically you can interpret your neural network as finding a basis functions, a set of trial basis functions, and then the rest, including the least squares, is part of your loss function evaluation. Okay? This is a way to improve the problem of the local minimum I was talking about. Okay, because here you find the global minimum with respect to these coefficients. Okay, so these are not the global basis functions, but at least once you have some basis functions, these coefficients are the global best ones. Okay, better than nothing. Fine. And this improves results, by the way. The second problem is very well known, the problem of regularity. If you have this problem, Poisson equation with discontinuous coefficients, and you solve it with pins, because it's a strong formulation, you get this solution. If you solve it with a weak formulation, like variational pins, you get this one. The correct one, the physically correct one, is the black one. The red one is the one you will get with traditional pins in the best case scenario. And this is just mathematics. There's nothing you can do to avoid it. Right? So you need some kind of weak formulation.
So with classical pins, you mean Monte Carlo integration?
It doesn't matter the integration you do. With traditional pins, you get this.
But what is traditional?
Well,
L2
L2 of the residual of Laplacian of human is f squared.
Applied to that.
The quadrature has nothing to do with that.
Oh, I mean,
Yeah?
yeah.
No,
It's
I mean,
going to influence all this.
it will influence things, but it will not find this thing because this is related to the weak thing. This, I mean, you are really solving a strong formulation even before you introduce any neural network. You're really solving a strong problem. So in the best case scenario, you will get this. If you get a bad integration, you will get something even worse.
All right.
And you're in more trouble. All right. So that's why we don't want to use pins, traditional pins, okay? And then it comes, that's why we move to variational pins and so on, okay? But then it comes the problem of integration, and that's what I want to talk about today. This is the central point, okay? And let me start with some examples. Basically, I have a loss, which is, as I mentioned before, residual in some dual norm. But this is always, whatever norm you use, this is always some integral. So it's the integral of something. That's it. And at some point, you need to discretize that integral. In other words, you need to select some integration points, integration weights, evaluate this thing, and you are going to use that. That's what you are really going to minimize. Okay? That's, I mean. So imagine we select a simple example. The solution is x to the power of 0.7. This is a very simple problem, Laplace equation, and we use the deep reach method where this integrand is this thing, 1/2 of u prime squared minus f times. Nothing really. That's what we obtain. This is a exact solution. This is the solution we obtain. By the way, this is a bad solution. That's my definition of bad. And if you analyze the loss, the quadrature we use here was some kind of Gaussian quadrature rule. The loss was going very well. It was going to the optimal value, and then all of a sudden it went to minus infinity. As you know, no solution can have any loss below this. Okay, so the only reason why the loss can go below is because I'm not evaluating my loss properly. I'm evaluating an approximation of the loss which is incorrect. Okay, so basically, because my error is here in this approximation. So to see this, I amplify this part. You see, these are the Gaussian points I had on this first element. And as you see here, the derivative is 0 in all the Gaussian points, almost 0. So it's taking this to 0. And then it's taking the values of this to be very large of the solution. So it goes to infinity. So 0 minus infinity, this goes to minus infinity. Okay. So basically, this keeps growing and I stop here. If you let more iterations, you go more and more and more. And you go all the way to minus infinity, the solution is worse and worse all the time. Trash. Okay? Fine. So deterministic quadrature rules, this is some kind of, by the way, overfitting. So solution is to use stochastic quadrature rules, okay? And we are slowing, going there. Fine. So the stochastic integration doesn't take a set of weights and points, but a probability distribution of these weights and points, okay? So each set of weights and points is one sample. And then I have more samples with different quadrature rules, okay? The simplest way to think of that is Monte Carlo, where you select arbitrary points, okay? Fine. Now, this is the expectancy of all these quadrature rules. Okay, so I have different quadrature rules. In other words, for each sample, I have n weights and n points, but I have many of those samples. Okay, and the average of all those samples, the expectancy is the average of all of them, is what I define here, is what the method Adam or stochastic gradient descent in general will converge to. Okay? So the stochastic gradient descent will not converge to the value of the integral, it will converge to the value of the average of all these stochastic quadrature rules. Okay? So if you want it to converge to the exact solution, you want this average to be exactly the integral. In particular, if you have a Gaussian quadrature rule, a deterministic quadrature rule like Gaussian, the average of this, since you always have the same quadrature rule, is the same as the quadrature rule of a single instance. It's just like evaluating once. So the evaluation of this one, let me see it here before, is not exact, it's just an approximation. So you are not converging to that, you're converging to this approximation. Okay? And the problem is that the neural network will learn a solution such that this approximation will be arbitrarily bad, will be really bad. Even if you are exact for polynomials up to degree 25, it will learn a polynomial of degree 127 that this will be a disaster, and therefore it will converge to whatever it wants. This is the problem. This is the real problem. The first one, there are many. Okay? So, okay. Since you may not believe me, let me make this with a very simple example and some theory. I consider, by the way, before that, an stochastic integration rule is said to be unbiased when this is true, that is when the average is equal to that, for any function IU. For any function, not for polynomials of degree 2, 3, 4, 5, for any function. Monte Carlo is an unbiased integration quadrature. All deterministic quadrature rules, all of them are biased. All of them are extremely biased. Okay. Because you never get this. There is no deterministic quadrature rules that tells you that this is equal for any function I of u. Fine.
Sorry, but there you are assuming global quadrature.
Sure. If you want to divide it in elements, the same story. You divide it in elements, and for each element, you need the same thing. It doesn't matter, it has to be equal.
No. But that problem that you have with quadratures is because we are using global quadratures and assuming that the function is a polynomial. It's not. That's clear.
No. If you use, I use always piecewise polynomials all the time. That's the previous example was with a piecewise polynomial, the same problem.
Okay.
Because you still are not exact.
Yeah.
Nothing prevents you from that. Okay. But I use all the time. I select small elements and then I do a quadrature there. Okay. Still, it's a problem. Okay. So imagine I select the following integration rule in -1,1 that is, by the way, is biased. It has 2 points and 2 weights. In 2 points is in the first subinterval, -0, 1, I select an arbitrary point. In the second one, which is -1, 0, I select an arbitrary point, okay? And this W1 and W2 are selected, so this is exact for polynomials of degree 1 or something like that. Okay, they're properly selected, the weight. Now, you can prove that for this quadrature rule, the expectancy of this quadrature rule is not I of x times dx, it's I of x times this kernel, which is given by that. In particular, this is not 1. Okay? Since you can prove that, you can show that you converge to this thing. And this thing is not what you wanted. This is not I of x dx. It has this term. And therefore, you converge to something different. And you can prove, this is a proof indeed, that for problems like deep pins or deep reads, you converge to an incorrect solution. And you have, I can do numerical experiments. I will show it in a second. You just convert to something different. You convert to something different. That's not nice. It's not what you want, okay? By the way, this corollary doesn't apply to pins. And this is what I'm going to talk a lot in the next few minutes. And the reason why it doesn't apply to pins is because in pins, in the limit, this thing is 0. So even if you multiply 0 times n of x, this is 0, and then things are slightly different. This is what I want to get. This is what I want to get. Okay, but let's go slowly. Okay. So by the way, if you consider an unbiased integration rule, you need to select x2 equal to minus x1 here. And then everything works. Then this nx becomes 1 and everything works. Right? So such a simple change makes things better. Now, there are other problems that where bias appears. In VPNs, you are doing this minimization of the residual. So you have the multiplication of the residual, or if you want the residual square. Okay? When you multiply two things, the expectancy of the multiplication is not the same as the multiplication of the expectancies in general. And this also applies to robust VPs. Okay, nothing changes. The same story. Okay? So you need to make this equal. These ones need to be sampled with a statistically independent sampling. In other words, you need to do two different samples for each sample, which means double the cost. Okay, not so bad, but still to double the cost. All right. Of course, this is only the square. If you need to invert something, then you are done. Because the inversion is, you cannot maintain the expectancy of the inversion. If you have the inversion of some matrix or whatever, you adjust this. Fine. So let me show you this with a very simple example. Okay, the example is Laplace equation 2D. The solution is very simple. Okay, and this is how you convert iterations versus the error, relative error, if you use unbiased integration and the unbiased product, that is the statistically independent samples. You get this red curve that converges to 0. If you have something biased, either the product or the integration rule, you get these three things. You don't convert. That's it. You don't convert. Life is bad. Okay? So you need stochastically unbiased integration rule. That's number one thing. Now let's go with the second thing, which is much more delicate. The second thing comes in terms of variance. Okay, so you have the first moment, which is called the expectancy, the second moment, which is the variance. The expectancy is the average of the evaluations of your integral, okay, of the samplings of your integral. And it should be exactly the same as your integral. And the variance measures how each sample of the integral, what is the error you have with respect to the correct integral, okay? Because if my exact integral is 5, and my samples are 4 and 6, okay, the average is 5, I'm fine, okay? But also the error of each sample is important, because if I took 1 and 9, my average is also 5. But you know, the error of each sample is much bigger, okay? So, you can prove that in gradient descent, if you want an error epsilon, your computational cost grows as 1 over epsilon. But in stochastic gradient descent, it is much higher. It's 1 over epsilon plus the variance divided by epsilon squared. So if the variance is large, epsilon is a small number, this is a much larger number, and the convergence deteriorates a lot. You converge, but you converge very slowly, okay? Because you're not computing properly the direction of the gradient in your stochastic gradient descent. Okay? Fine. So, the second trick is I want to go with the variance to 0. And there are two ways of doing that. First way is something called passive variance reduction technique. I'm going to explain in a second. Second way is active variance reduction technique. And this is the part I will explain at the very end, and it will go very fast, okay? I want to go first into the passive variance reduction technique. And let me explain this with a very simple example before I go with something more different. Can I go into the blackboard for a minute? Okay. Imagine I have Laplace equation. Okay? Can you read it here? Can you see this? Okay, good. This is Laplace equation, and this is my loss in pins. Do you agree? Okay. And this is my loss in deep roots. Correct. Okay. Imagine I'm lucky enough and I convert to the exact solution. Okay, my life is good. I'm on the exact solution. If I'm on the exact solution, let me call the exact solution, I don't know, with a star, okay?
Probably there should be a plus in the first.
The what?
Probably a plus in the
Where
first.
is the plus? Here?
No.
Here?
There.
Here?
Yeah.
A minus, yeah. Ah, you're right. Yeah. Sorry.
Don't know what you're after, so it might bother. You don't know yet. Go ahead.
No, yeah, this is. Okay, imagine I'm on the exact solution, okay? But I want to do one more iteration of a stochastic arrival distance, one more iteration. And now I need to do an integration rule of that. How many points I need on my integration rule to this to be a good approximation of that? It's a tricky question. Simple answer. How many points I need to get a good approximation of that integral? It's at 1. This
Zero.
is exactly 0.
Yeah.
So how many points I need to integrate this exactly?
No point.
Well, 1 point. Let's make it simple. Let's make 1 point. Okay. So with 1 point, this is not an approximation. This is equal. Okay. What about this? If this is in H01, okay, you can do integration by parts, and therefore this will be like Laplacian of U star times U star minus F times U. Okay, this is F. If this is in, if this is in H01, I'm doing integration by parts. I don't have boundary terms. This is F. So this is really this thing. And this is, I think I did something wrong with the signs. I don't remember. Anyway, this should be like minus 1/2 of F U star. How many points do I need to integrate this correctly? Imagine that U is sine of 100x. How many points I need? Many. 300, 500. What about in 3D? 300 cube. 300 cube is like 27 millions. That's a lot. What happens if I don't do 27 million points and I put less? Well, my gradient will not be good. Even if I found the exact solution, I will get away. It's a bad thing. Okay? So, okay, what happens on the limit before you arrive to the exact solution? That this integrand becomes smaller and smaller. And because it becomes smaller and smaller, the variance, the error of the integration, becomes smaller and smaller. While in this method, you don't become smaller and smaller, and the error of the integration remains constant, no matter how close you get to the exact solution. This makes the other method much more expensive. Now, this is deep rich. If you do B-pins, same thing. This is pins. If you want to get a weak formulation that has the same property, you need to go to fossils. That's why I'm going to fossils now. Because I don't want the problems of pins. I don't want the problems of integration. Okay? So let me show this with a little bit more formalism here in a few slides. Okay? This is my main point. After that, I can get quiet whenever you want. Okay? I can stop whenever you want. Now, so in machine learning, there is something called interpolation property. This is not the typical interpolation we're used to. Okay, this is basically it says that if the losses can be seen as a sum of data points, let's say, it verifies the interpolation property if the exact solution minimizes every function, every sample simultaneously. Okay? If you try to do that with extension to PDEs, this is very difficult because you can have singularities at some point and things become really difficult. So the way we propose it is what we call a quasi-interpolation property that says that if you have a PDE of this type, it's an integral of something, the stochastic estimator satisfies the quasi-interpolation property if this derivative it's 0 with probability 1. Okay, this is equivalent. What it guarantees is that you reduce the variance automatically near the optimum. That is, by selecting a proper loss, the variance reduces automatically in a passive way. You don't need to do anything. Okay? This is the whole point. By the way, let me show it with this very, I find, extremely nice example. It took me a while to understand it, even if it is very simple. But I'm going to propose you two methods. One of them is H1 minimization of the error, and the other one is the deep reach energy. I can prove that these two things are not similar, they are equal. It's very simple to see that if this solution is in H01. You have this square is this thing, okay? This square is a constant because it's not, you are not optimizing the exact solution, it's a constant, okay? And 2 times this times that, you do integration by parts if you are in H01, and you're now having Laplacian of U star, which is F times U. So these two things are exactly the same thing. Okay? That implies that if I have exact integration, if I minimize this or I minimize that, I get the exact same solution at every iteration, no matter what. Because I'm minimizing the exact same thing. Period. Okay? Under exact integration, I do exactly the same thing. Well, but the difference is that at the optimum, this has this quasi-interpolation property, and therefore you have 0 variance, and this doesn't have this quasi-interpolation property, you will have very high variance. So, let's do the example. Deep reach method, this is the way you convert, H01, this is the way you convert. For a very simple solution. Stratified Monte Carlo. This is only the result of integration. Or if you want, the result of having this passive variance reduction property here and not having it here. Basically, this stagnates. At some point, your integration error dominates, you're done. There's nothing you can do about it. Okay? And again, I insist, if you put exact integration, these two curves are exactly identical. Exactly, not close, exactly.
That you have the exact solution is just for the experiment, right?
The what?
That you have the exact solution.
Yeah.
You start just.
Yes, exactly. Yes. In practice, you cannot do this because you don't have that. And therefore, you need to go to either beans or fossils or something like that has this property, but yeah, I mean, in practice. But the thing is very illustrative. I mean, it really shows that the integration is there. There is no other thing that affects here other than integration. Okay, so quasi-interpolation is important. It allows automatic variance reduction and remain stable near exact solutions. Without it, well, if you have a good integration, you are fine, but otherwise you have problems. Okay, and it's much more sensitive to this bias because of what I explained before, that when the integrand tends to 0, when this thing tends to 0, even if I multiply it by this n of x I showed before, still fine. The bias will not kill you because you still go to 0. But if it doesn't go to 0 and you multiply by some n, you get to a completely different solution. So it's really unstable in the presence of bias to use these things. Really unstable. That's a problem. So, okay, so this was the main point. The rest is, okay, I was talking about these passive variance reduction techniques. That is, how I select a loss that the variance goes to 0. Now the question is, okay, I still need a good integration rule to to integrate more or less properly in the pre-asymptotic regime and so on. So you can use many techniques. We propose 3 of them here, by the way, and I'm going to show them very fast. But one may come up with different integration rules. Okay. The first thing is what we call unbiased high-order stochastic quadrature rules. The idea is the following. I'm going to select a set of integration rules that is unbiased and such that integrates exactly polynomials up to degree 3 or 4. How are we going to do that? The same way you construct the Gaussian quadrature, we are going to construct an infinite number of quadrature rules that are exact on polynomials. This is really very basic. I may really skip it altogether, but the idea is in Gaussian quadrature rule, you have a system of 2n unknowns with 2n equations, because you have point locations and weights. This in 1D, in 2D and 3D is slightly different, okay? And you basically solve this nonlinear system of equations, you get the quadrature points, the quadrature weights, and you're in here, we are going to do the same, but we are going to add one random distribution point. And therefore, we are going to add one less unknown. And therefore, we make the system square so we can solve it. And then we solve it with some neural network. We do a neural network to produce all this infinite number of integration rules, and then we're done. This looks difficult, but it's really simple. And then we make it unbiased, and it becomes technical, but it's very simple. Anyway, the entire point is that with the deterministic integration rule, you cannot stagnate. With the stochastic integration rule, you go to 0 much faster, everything's better. Okay. The regularity conforming, this is another thing. If you have a solution with a discontinuous gradient, it's something like that, you have a problem, which is that at the discontinuity of the gradient, you get this kind of Gibbs phenomenon, which is super difficult to integrate. Okay? The solution is basically to introduce an architecture that explicitly contains the same discontinuity as the solution. This is like what finite element does. Finite element, what you do, you do a conforming grid, means that when your materials are discontinuous, you put a finite element basis function that will have a discontinuous derivative, and then you will adjust to it via the variational formulation. You could do the same thing. And if you do that, you remove the Gibbs phenomena at the expense that you need to know beforehand where the singularity is located. You don't need to know the jump of the singularity because this is a trainable parameter, but you need to know where it is. Right? Actually, this is not a singularity, this is a discontinuity. When you have singularities, you can do something similar, by the way, but this is also a discontinuity in 2D, you can do something like that. Well, smooth neural network converges like this. If you put the discontinuity in the proper way, you converge better because you integrate better and so on. And you approximate better and everything's better. Yeah. What is Herriko? The what? Herriko is what we call regularity conforming neural network. Let's call it somehow.
Yeah.
Okay. Another thing you can do is in the traditional pins, you can add, by the way, once you have this architecture, you can add the jump of the flux, because now this term, I mean, you could always add this term. The problem is you cannot always evaluate it. If you have an architecture that is discontinuous, I mean, whose gradient is discontinuous here, you can really evaluate that. So therefore, you can use traditional pins with this additional term in the loss, and everything works. This is like, I mean, imposing where the discontinuities are by hand, basically. Okay. And well, it works much better. I mean, the errors go from 5% to 0.1, everything looks much nicer, and so on. And the other thing you can do is another option. I mean, there are many options. I'm only talking about 3 of them we are working on, okay? Is go into this world of probabilistic, or I don't know, the people who do Monte Carlo, or is this probabilistic, is the area of mathematics, probability, or it's not the statistics, more probability. Okay, and you can do something called important sampling, which basically is, you know, In the traditional Monte Carlo, you approximate this integral by a sum of evaluation of this integrand in a uniformly distributed sample of points. In important sampling, you kind of do a change of, it's like doing a change of variables in the traditional world of integration. And basically you divide by this Q, which is they call proposal distribution, and then you select this X that follow this proposal distribution, and this is equivalent, okay? And the idea is that if your proposal distribution is proportional to the integrand, then you can prove that the variance is 0 and your integration is exact, okay? And then the entire trick is how you find this proposal distribution. And there are a number of techniques. I mean, I don't want to get into that because this is more about probability. And basically, the idea is that your proposal distribution should be like the integrand, okay? But this is a different problem. It has some advantages, some disadvantages, and so on. And then we propose some things of doing some parametric importance sampling, and blah, blah. And it works much better, by the way. This is with the probability importance sampling. The variance goes much smaller in the gradient, which is where it is important. The variance of the gradient is much smaller with this thing. And as a result, you converge much better. The green one is the one we propose. The other ones are the traditional ones with Monte Carlo. You converge much better. This is the deep rich method, I think. Yeah. And then you can, I mean, many people ask me, oh, why do you want to use neural networks altogether? Finite elements are much faster. Yeah, finite elements are faster so far. But for parametric PDEs, you can solve a parametric PDE problem at the expense of solving a single PDE problem when you do neural networks. It's really fast for solving parametric PDEs. Not for traditional one, but for parametrics as well, which is important for inverse problems and so on. Okay. And then we have a lot of things. I think this is getting too much. So since I don't want to, I mean, we have results here and there, but it becomes more and more complex. Okay? Same ideas of integration apply, and you can solve them. Actually, the result with parametric PDEs, the only thing that is impressive is we get much smaller errors. You have a PDE, and you select a single parameter, and you solve it, we get errors of 1%. But if you make it parametric and we solve the parametric one, and then we look at this particular one, typically we get errors much smaller, like 0.2, 0.1. Why? Because it's kind of stabilizing the whole thing. It's kind of finding better this global minimum. It's amazing. It's amazing. So this is where the value is of neural network. Okay? Or we expect the value will be at some point in our life. And at the same cost. That's incredible. For the same cost, I get better solutions. We're thinking of this as parametric. Anyway, okay, and we have many examples of that. I don't want to go into that 2D with discontinuities and blah, blah. I think the whole point is we need a stochastic unbiased higher order integration rules. This is the conclusion. A stochastic unbiased higher order integration rules. Or if you want, we need a stochastic unbiased integration rules with low variance. And then we need also losses that have this quasi-interpolation property. So the variance goes to 0 as you approach the solution. So we need active variance reduction and we need passive variance reduction. With all of that, when you have discontinuities and singularities and things like that, you still need additional things. Otherwise, integrating the discontinuities is very difficult. Or the singularities. You either need to do some kind of this or important sampling or something like that. Otherwise, it is. And we're still there. I mean, we don't, it's difficult. I mean, we don't know how to solve any true problem. Makes sense? Is it understandable?
Okay, thanks, David. Have time for questions.
Yeah, maybe just to make a resume of the first part, you say basically the messages you have to use like a minimum residual formulation for your problem to be able to possibly have like what you told, like what you have in
Yeah, but when you say, you said minimum residual.
Yeah.
Yeah, but sometimes when you talk about residual minimization, then you introduce a test space, and then the integrand, I mean, you don't have this quasi-interpolation property. So it really means the residual, the true residual. Like in pins, that is the true residual. There's no multiplication by test function. Or in fossils, where you have the true residual, but you're not multiplying. In the moment you start multiplying by test functions, you may lose this quasi-interpolation property. The key point is the quasi-interpolation property. That's the whole thing.
Okay, so you have to impose more, say, regularity for the residual. Right? Because
not in fossils. In fossils, you don't need to impose regularity.
Yeah, fossils.
In fossils, that's why I want to go to fossils.
Okay. And actually, that is for me pins. These people always use first order formulation.
Pins for first order is fossils, I agree.
Yeah.
So this is the, but pins for first order. The traditional pins of Karmiadakis is that thing. This is the, I mean.
But people doing pins today are doing everything.
Well, people can do whatever they want, but 99% of the people, which comes from the engineering world, that they talk about pins, they refer to this always. They never think of first order equations, they always go there. So.
At the beginning, you talked a lot about the distinction between looking for local minima and the global minimum. So where does this issue appear here? Didn't it appear because of the problems you're considering, or because in a numerical experience you're successful, you always converge to the exact solution, I understand.
No.
You never had the problem of local minimum?
Yeah, I mean, at some point, things stagnate. I mean, you start converging and you stop. This always happens. The issue is that in our case, it happens later because we do good integration. If you do bad integration, it happens very early.
But this case of the errors 10 to the minus 2, that's relative errors 10 to the minus 2, that was assuming to be then close to the optimal, to the exact solution?
You hope so, yeah. You never know. This is one of the issues, you never know. Things stop. I mean, that's why.
So you don't have a model case where you can really somehow test to distinguish between local and global minima.
This is a good one. Okay. Because in here, you know that if the integration will be exact, both things will be exact.
Yeah.
And the blue one is converting very well. By the way, the blue one is converting very well also because we're using stochastic antecedent with momentum. We are not even putting Adam because we know many things about this problem. Let me put it this way. And therefore, you converge really nicely. At some point, it will stop because at some point, you also don't have resolution in your neural network. It's not an infinite approximate. It has to stop. But so far, you see it very well. Anyway, this H1 error is 0.7%. In the other thing, you're stopping at 6% or 5%. It's not so small. It's not so small. This is what happens. Yeah, but one of the main difficulties of neural networks is precisely that. When you stop, you never know where the problem is.
Just wondering about a very particular model probe where can someone investigate this relationship and whether you're in the neighborhood of the global minimum or the neighborhood of the local minimum.
Yeah, you don't know. For example, if you try to solve Helmholtz, it's very, very super typical that the solution you obtain is 0. Because this is kind of a very strong local minimum. Super typical. And if you do something very hard code, it will produce you 0. Or it will produce some starting of the wave and then 0. That's the first thing it will do all the time. And this is like a local minimum. And once you get the 0, you don't escape from there.
You have a question in Zoom. But I'm not sure how to get it. ¿Me ayudas con una pregunta que está en Zoom?
Oh,
No sé si se puede
I didn't realize. Who's Mashek?
This is
not our Mashek.
Yeah.
hidden participants.
Who's Mashek?
Hi. Can I ask question?
Oh. Yes.
Yes. So first of all, very interesting talk. Thank you very much. I have the following question because I think all these problems is because your activation functions are like non-polynomials. What if you use like polynomials or the B-splines as activation functions? Because even the catenation of the polynomials or B-splines is exactly integrable.
If you use polynomials, if they are of very low order, you could do exact integration if you want. But by the way, you are probably never using polynomials, you're using piecewise polynomials. And piecewise polynomials with some breaking lines or breaking hyperplanes that you don't know where they are. And therefore, you cannot do the exact integration unless you know where they are. If you know where they are, which is what Chris van der Zee is trying to do, then yes, you could do exact integration. By the time you implement an exact integration of such a complicated thing, you're out of business, basically. And if you make a very simple architecture, then you are not approximating anything, so you are also out of business.
So it's very expensive.
Yeah. If you want to approximate complex things, yes. If you are trying to approximate very simple things, okay, you could do it. I mean, Chris van der Zee is trying to do that, but I find it extremely difficult. And also there was, I think Kali was doing something like that. But this is very, very difficult. I mean, they only consider very simple things with one layer, 1D. In 2D, they already have problems. 3D is out of question. They need to find out the breaking lines. Terrible. To me, I mean, I'm fine with the options, but.
Okay. Thank you very much.
Thank you, Maszek. Regard. I see you soon.
See you soon. Yeah.
Thank you for your talk. I was wondering, I come from a different world. I'm not very familiar with much PDE type of problems, but I do work on developing adaptive importance sampling methods more applied to Bayesian problems, experiments, right? And one of the problems of those schemes is that it's very difficult to find a good proposal. The proposal has to cover all the support of your samples, otherwise the weights jump and you really get stuck, and it's very difficult to avoid those regions. So I was wondering, you mentioned that there are techniques to find good proposals in your context. Could you explain a little which are
the
those?
technique is the following. I got a person who is extremely good on those things, and we hired him. This is the first technique, because I have no idea, okay? But I know you can use defensive importance sampling, you can do many things, so this weight explosion doesn't happen. And I didn't talk about any of that because this would be a completely different presentation, okay? But the whole point, and this is something I didn't emphasize before, the whole point is, I don't really care about integrating this properly. I was lying all the time. What it is important is to integrate the gradient of this with respect to the trainable parameters. Since the trainable parameters could be of the order of 10,000 or more, you need to integrate not one integral, but 10,000 integrals. And the issue is that the proposal distribution has to be 1. So you need one proposal distribution for 10,000 integrals. And that's what we are trying to develop, some kind of parametric proposal distribution. Because otherwise it doesn't work. Indeed, we got extremely, extremely good proposals to integrate this. And it was a disaster, because this was properly integrated, but not the gradient. And what you need for stochastic gradient descent is the gradient. You don't care about the loss, you care about integrating the gradient. It's a partial answer, okay? But this is very open research area. And that's why we hired the good guy.
Can I ask about because maybe I misunderstood this, that you say that the same happens if you use BPins, but I don't see why, because it's also something that is positive.
Because in BPins,
you are minimizing.
In BPins, in BPins, you end up with something like this, very similar to that.
Oh,
The loss is like that.
no, it's
If
that
phi-
square if you want. That term square. I mean, you are minimizing.
Yeah, but because this is a deep reach, this is a derivative of the reach. But if you think of the V-pins, okay, let me write it in the right way.
Yeah, that's right.
The loss of V-pins you have the sum or end of, I'm sorry, the sum or end of grand U grand Vm minus f times Vm of some xn, of this thing, sum or ends, and I think this thing is a square, isn't it?
Yeah, something like that.
So this is not point by point. It's
Yeah,
basis functions to basis functions.
No,
Not
just
point by
following
point.
your example, because you say that, okay, let's assume you have the solution.
This example,
So
if you have a exact solution,
that is true.
no.
Yes.
No,
Yeah,
no, no,
because
no, no, no,
the
no.
VMs belongs to the thesis space, right?
No, because you are, no. Because what you are fixing here is the xn.
Yeah, yeah.
So in the moment you fix the xn's for a finite set of test functions, you are not gonna get this thing to be 0 for every point. You're gonna get for each test function,
Okay.
you get the integral in space will be 0 for each test function. That I agree. But each point is not 0. This is the issue.
I see. Okay.
This is the main issue. And therefore, and then you will get negative things with positive things and it will kill you.
Yes. Okay. Yeah. Okay.
Any other question? No, let's say, la vida que es profesor.